Somewhere 124 light-years from where you're sitting right now, a machine folded like origami and launched on Christmas morning is staring at a single molecule. Not a planet, not a galaxy, a molecule. On Earth, that molecule is made almost exclusively by one thing: living organisms in ocean water. And James Webb just found a strong signal of it in the atmosphere of a world twice the size of ours. That is not the strangest thing it found this year. At the same time, on the opposite edge of the solar system, the same telescope pointed itself at a frozen dwarf planet most of us were taught to stop caring about in school, and it found something in the ice that has planetary scientists quietly rewriting their models. And billions of light-years passed that, in light so old it left its source before Earth had finished forming, Webb found galaxies that are, by every rule we have, impossible. Too big, too bright, too organized, too soon. 3 separate mysteries. 3 separate corners of the universe. All discovered by the same machine in the same 18 months, and all pointing toward the same unsettling possibility. Some of what we've been teaching as settled science for the last 50 years might simply be wrong. Stay with me, because by the end of this you're going to understand why scientists keep using the word impossible, and why that word should make you more excited than afraid. Let's start with what this machine actually is, because it matters for everything that follows. James Webb is not a bigger, better Hubble. It's a different kind of eye entirely. Where Hubble mostly sees the same visible light your own eyes do, Webb sees an infrared heat, essentially stretched and dimmed by billions of years of cosmic expansion until it arrives here as a whisper. That single design choice is what lets it do 3 things no telescope before it could do at this scale. Read the exact chemical fingerprint of an atmosphere trillions of miles away, see straight through the dust that used to hide the birth of stars and planets, and look so far back in time that it's effectively watching the universe's baby pictures develop in real time. Keep that in mind, because every mystery in this video comes from Webb doing one of those 3 things somewhere it wasn't supposed to find anything interesting at all. It took nearly 3 decades to build, cost roughly $10 billion, and had to unfold itself in space like a piece of origami, because there was no rocket on Earth large enough to launch it fully assembled. A sun shield the size of a tennis court had to snap into place perfectly, on the first try, 100 million miles from any human hand that could fix it if something jammed. Engineers called it the Year of Terror, hundreds of single points of failure, any one of which could have ended the mission before it ever opened its eye. It didn't fail. It settled into a stable orbit around a gravitational parking spot called the second Lagrange point, roughly 1 million miles from Earth, always facing away from the sun, always staring outward into the dark and the cold, exactly where its name is TOI 199b, and before you forget that name, here's why it matters. Picture the planets in our own solar system for a second. The big gas giants, Jupiter, Saturn, are cold. Deeply, permanently cold, because they orbit so far from the sun that warmth barely reaches them. The close and giant planets we found around other stars are the opposite extreme. Bloated, blistering worlds astronomers nickname hot Jupiters. Some of them hot enough to vaporize metal on their dayside, while their nightside stays locked in permanent darkness. For years, that was the entire pattern. Giant planets came in 2 flavors: frozen or scorched. Nothing in between. Nobody had found the in-between world, because for most of the history of exoplanet science, we didn't have an instrument sensitive enough to even look for one. TOI 199b broke the pattern. It's roughly the size of Saturn, but it sits at a distance from its star that gives it something almost nobody expected to find on a world that large. A temperature range close to Earth's. Not tropical. Not frozen. Comfortable in the way our planet is comfortable, at least compared to everything else giant planets are supposed to be. Picture standing on a floating platform above its clouds, no ground to stand on because it's a gas giant, but if you could, the air around you wouldn't kill you in seconds the way it would on almost every other giant planet we've cataloged. And when Webb split that planet's light apart into its component wavelengths, a technique called spectroscopy, which is really just reading the fingerprint that molecules leave in starlight as it passes through an atmosphere, it found methane. Clean, clear, undeniable methane, sitting in an atmosphere at a temperature where, by older models of planetary chemistry, methane wasn't supposed to survive in those quantities at all. Here's why that detail matters more than it sounds. Methane breaks down quickly under starlight unless something is actively replenishing it. Its presence at that concentration, at that temperature, means either the planet's internal chemistry works in a way researchers hadn't modeled, or something down in that atmosphere is topping the methane back up faster than sunlight can destroy it. Neither explanation. Using infrared instruments sensitive enough to read heat signatures across billions of miles, Webb captured the clearest thermal picture of Pluto and its largest moon, Charon, that anyone has ever recorded, measuring, for the first time, exactly how heat moves through Pluto's hazy, layered atmosphere. And that haze isn't just sitting there passively, some inert leftover fog. It's actively regulating Pluto's climate, the way a thin blanket of clouds regulates temperature on a much larger, much closer moon of Saturn called Titan, trapping heat in some layers, venting it in others, behaving less like dead air and more like a working thermostat. A dead dwarf planet, 4 billion miles from the Sun, turned out to have functioning climate machinery running quietly the entire time nobody was watching closely enough to notice. Then it got stranger. Webb turned its instruments on Charon, Pluto's giant moon, and detected carbon dioxide in observation after observation. Webb has photographed galaxies that existed just 3 to 500 million years after the Big Bang, and they are enormous, structured, glowing with the light of mature stars, the kind of light you'd expect from a galaxy that had already had billions of years to grow up. By the standard model of cosmic growth, galaxies that size, that early, simply should not exist. It's the equivalent of looking at ultrasound footage expecting to see a first trimester embryo and instead finding a fully grown adult, already standing, already walking around, already old enough to have opinions. Astronomers have started calling them, only half-jokingly, impossible galaxies. And it isn't just one anomaly scientists can wave away as a fluke or a measurement error. Researchers have gone on to document an active, ongoing merger of at least 5 separate galaxies, colliding and combining 800 million years after the Big Bang, spreading heavy elements out into space through the wreckage of that collision like debris scattering from a car crash filmed in impossibly slow motion. Processes that current models said needed well over 1 billion years to even get started were already fully underway less than 1 billion years in. Somewhere behind that anomaly is a giant galaxy that, according to Webb's own data, appears to not be rotating at all, sitting almost perfectly still in a universe where nearly everything spins, where rotation is supposed to be one of the few universal rules every galaxy obeys, for reasons nobody has fully explained yet. Every one of these findings forces the same uncomfortable question. What did we get wrong? Some astronomers think dark matter, the invisible material that makes up most of the universe's mass but has never once been directly detected, only inferred from its gravity, behaved differently in the early universe than our models assume, clumping together faster and pulling ordinary matter into galaxies ahead of schedule, like scaffolding going up faster than anyone planned for. Others think star formation itself, in that first chaotic era, was simply far more efficient than anyone modeled, turning raw gas into stars and structure at a speed our equations don't currently allow, no matter how many times theorists rerun the math. Nobody agrees yet. That's not a flaw in the story, that disagreement playing out in real time, in real published papers, in real arguments at real conferences, is the story. And this is where all 3 threads, the impossible planet, the not-so-dead dwarf world, and the impossible galaxies, quietly braid back together into one bigger question, because there's a 4th discovery that connects them all, and it's the one that should actually keep you up tonight. That planet with the biosignature molecule I mentioned at the very beginning, the one that opened this video, has a name, K2-18b. It's over 8 times the mass of Earth, orbiting a small, cool star roughly 124 light-years away, sitting inside what astronomers call the habitable zone, the narrow, precise distance from a star where liquid water can exist on a planet's surface without boiling away or freezing solid. Webb's instruments picked up something in its atmosphere called dimethyl sulfide. On Earth, this molecule is produced almost exclusively by marine phytoplankton, living ocean organisms, the same base of the food chain that feeds nearly everything in our oceans as a metabolic byproduct. There is essentially no known way, in current chemistry, to manufacture it in meaningful quantities without biology being involved somewhere in the process. The signal is real. It has been detected. But, and this matters because a script that doesn't tell you this part is lying to you, it currently sits at what scientists call 3 sigma confidence, not the 5 sigma threshold the field requires before calling something a confirmed discovery rather than a strong, tantalizing hint. 3 sigma means there's still roughly a 1 in 1,000 chance it's a statistical fluke, a shadow in the data rather than a signal. 5 sigma is the gold standard, the one in 3.5 million bar physics uses before it lets a result rewrite a textbook. K2-18b hasn't crossed that line yet. Webb has more observing time scheduled specifically to try, more hours pointed at that one small star, waiting for the universe to either confirm or quietly take back what it seemed to be telling us. But sit with the shape of that sentence for a second. The strongest potential biosignature ever detected on a planet outside our solar system is currently sitting in a queue, waiting for enough telescope time to confirm or kill it, and most of the people watching this video have never heard its name before tonight. Here's the layer underneath all 4 of these stories, the part that isn't really about planets or galaxies at all. Every single one of these discoveries, the giant planet that shouldn't hold methane, the dwarf planet that shouldn't have working chemistry, the galaxies that shouldn't exist yet, the molecule that shouldn't be there without life, is a place where reality quietly refused to follow the script we wrote for it decades before we had an instrument sharp enough to actually check our work. We built our models on incomplete information and then, slowly, without quite meaning to, mistook the models for the truth itself. Webb isn't handing us answers wrapped in a bow. It's handing us the uncomfortable, thrilling realization that we've been reading an unfinished book and confidently calling it finished. That's actually the oldest story in science, dressed in new clothes. Every leap forward, the telescope that showed Jupiter had moons of its own, quietly ending the idea that everything had to orbit Earth. The instrument that first revealed the universe was expanding rather than fixed and eternal. The observation that proved space and time themselves bend under gravity started the exact same way. Not with a triumphant discovery of something we expected to find and simply confirmed, but with a small, stubborn piece of data that refused to fit the box we'd already built for it. Webb is producing that same small, stubborn refusal in 4 different places in the sky at once, right now, and every single one of them is still actively being investigated while you watch this. So here is where this actually leaves us. A 4-watt refrigerator light of a spacecraft named Voyager 1 spent decades teaching us the universe was stranger at its edges than we assumed, one faint radio signal at a time. Now, closer to home and further back in time simultaneously, a 6.5-meter gold mirror parked a million miles from Earth is teaching us the same lesson from 4 directions at once. A planet that shouldn't be able to keep its atmosphere, a dwarf world that shouldn't have a working climate, galaxies that shouldn't have grown up this fast, and a molecule that, if it survives one more round of observation, would be the single most important scientific result in human history. None of these 4 mysteries are settled. That's not a disappointing ending, that's the honest one. Real science doesn't wrap up in a neat bow at the 20-minute mark, no matter how satisfying that would feel. It leaves a stack of open questions on the table and dares the next observation to answer them. Webb has more observing time scheduled on every single one of these targets over the coming year. The methane on TOI 199b will either get explained by some chemistry we haven't modeled yet, or it will get stranger. The Kuiper belt will either turn out to be full of quietly active worlds humming along in the dark, or Pluto will turn out to be a strange exception. The impossible galaxies will either force a genuine rewrite of how the early universe worked, or reveal some subtlety in our instruments or our math that we simply missed. And K2-18b's biosignature will either climb toward 5 sigma confidence and become the most consequential number in modern science, the number that changes what it means to be alone in the universe, or it will fall apart into noise and become a footnote and a lesson in patience for everyone watching tonight. Somewhere out there, right now, while you finish this sentence, that 4-watt adjacent, $10 billion mirror is still listening, still measuring the faint fingerprints of starlight bent through alien air 100 light-years away, still quietly building the case that we understand far less about our own universe than we confidently assumed a decade ago. And whichever way each of these 4 questions eventually resolves, one thing is already certain, and it's the one thing worth carrying with you after this video ends. The universe was never obligated to make sense to us on our first attempt at explaining it. It only ever